Hi, in this video, we will be discussing about moments and center of mass, which is the second concept in section 8.3, chapter 8, section 3. A main objective here is to find point P on which a thin plate of any given shape balances horizontally. The point is called the center of mass. So if you consider a thin plate and you are going to find out a point, and if you hold in that point, the thin plate should balance. That point is called the center of mass. So before we get into that, we are going to learn some basics. If there are two masses, M1 and M2, that are attached to a rod of negligible mass on opposite side of a fulcrum is shown here, then there are two masses. Then if D1 is the distance between the mass M1 and the fulcrum, and D2 is the distance between mass M2 and the fulcrum, then the rod will balance if M1 D1 equal to M2 D2. The mass multiplied by the distance D1 is mass M2 multiplied by distance D2. This is the basic principle of a rod of negligible mass balancing. The same idea can be applied if there are two masses and we consider an origin here, and x bar is where the position of the fulcrum is. Then at x1 the mass M1 is placed. At x2 mass M2 is placed. The total mass is going to be M1 plus M2. Now if you apply the same rule that M1 D1 equal to M2 D2 that we did before, so now we are going to consider M1, the mass, multiplied by the distance between the mass M1 and the fulcrum, which is in terms of, because the origin is placed here, it is actually going to be, the distance is going to be x bar minus x1. And then on the other side, it's M2 multiplied by x2 minus x bar, because we are measuring the distance from the origin. So it's x2 minus x bar, that will be your D2. So this distance here is D1, and this distance, which is x2 minus x bar, is D2. So M1 D1 equal to M2 D2. Then in this, if you bring in, if you distribute, you will have M1 x bar minus M1 x1 equal to M2 x2 minus M2 x bar. If you bring in all the terms involving x bar to one side, so it is M1 x bar. If I move this to the other side, it will become M2 x bar. Then the terms involving, not involving x bar would be M1 x1 and M2 x2. So it is equal to M1 x1. If you take the left hand side to the right hand side, the negative will become positive. That is M2 x2. If you isolate the x bar, if you common factor the x bar, you get x bar multiplied by M1 plus M2 equal to M1 x1 plus M2 x2. Then by dividing by the total mass, M1 plus M2, M1 x1 plus M2 x2 divided by M1 plus M2, that will be your x bar, which is where the fulcrum is balanced at. So it is kind of similar to the idea of finding the weighted mean. So it is M1 x1 plus M2 x2 divided by the total mass. So if I make it, if I make a generic generalization of the above result, We have a system of n particles with masses m1, m2, etc., mn, located at different points x1, x2, etc., xn on the x-axis. It can be shown similarly that the center of mass of the system is located at x bar equal to sigma mi xi over sigma mi. There we had only two masses m1, x1 and m2, m1 and m2. Here we have n masses and there are n points. So it will be sigma. So if I expand this, it's going to be m1 x1 plus m2 x2 and so on up to mn xn. That will be the numerator, divided by the denominator, the total mass, which will be m1 plus m2 and so on up to mn. So in a concise way, we write this as sigma mi xi over sigma mi, where sigma mi, the sum of the masses, is going to be the total mass m. Now, if we consider again, we extend this idea to two-dimensional particle masses, then we will have, if x1, x2, etc., x2, y2 and so on are in the xy plane, the moment of the system about the y-axis, so we call it m equal to sigma mi xi, is called the moment of the system about the origin. That's what we used in the earlier discussion. So if we consider the same thing about a two-dimensional plane, and we consider n particles, which are x1, y1, x2, y2, x and yn, placed at these points with these masses, and then we get moment about the y-axis. We consider the moment about the y-axis, so we have to multiply the distances horizontally. So moment about the y-axis is sigma mi xi, which is moment of the system about the x-axis would be mx, which will be moment of the system about the x. So in that case, we will be considering the distances vertically. It will be mi yi. So moment of the system about the x-axis is mi yi. So its x-axis will be mi yi. Then moment about the y-axis would be mi xi. So as in the one-dimensional case, the coordinates x bar, y bar of the center of mass are given in terms of the moments of the formulas. X bar would be my, moment about the y-axis, divided by the total mass, and y bar will be moment about the x-axis divided by the total mass, where m is the total mass, sigma mi, and my, this my stand for moment about the y-axis, which sigma mi xi, and then mx, which is a moments about the x-axis, which is sigma mi yi. We'll check this example, which is based on the moments. Example number 3 in your handout. Find the moments in center of mass of the system of objects that have masses 3, 4 and 8 at the points -1, 1, 2, -1, 3, 2 respectively. Here we are asked to find out the center of mass, and then you are given the masses m1, m2, m3 or 3, 4 and 8, and you are given the points where the masses are located at, which are x1, y1, x2, y2 and x3, y3. Right? So these are x1, y1, x2, y2 and x3, y3. So the formula that we found, we need to find x bar and y bar. X bar is moment about the y-axis divided by the total mass. Y bar is moment about the x-axis divided by the total mass. So we have to find out these two values. So let's start off with moment about the y-axis. That will be sigma mi xi. So that will be m1 x1 plus m2 x2 plus m3 x3. m1 is 3, m2 is 4, m3 is 8. These are the masses. So it is 3 times x1 equal to -1 plus m2, which is 4, times second x coordinate, which is 2, plus m3, which is 8, multiplied by the third x coordinate, which is 3. So it is -3 plus 8 plus 24, that is going to be 29. So m sub y equal to 29. Now we will find out m sub x, which is sigma mi yi, moment about the x-axis, which is m1 y1 plus m2 y2 plus m3 y3. Now we will multiply each mass by its corresponding y coordinate. So 3 is the first mass, multiplied by its y coordinate, that is positive 1, plus m2, which is 4, multiplied by its second, the y coordinate, which is -1. Third mass, which is 8, multiply by its y coordinate, that is a 2. So that is going to be 3 minus 4 plus 16, that is 15. Now going back to step number 1, so x bar, which is the center of the x coordinate of the center of mass, which is x coordinate of the center of mass, that is going to be my over m. My is 29. 29 over 15 total mass, which is m1 plus m2 plus m3. So m1 plus m2 plus m3, that is the total mass, which is 3 plus 4 plus 8, which is equal to 15. So this is our total mass. So that is the x coordinate, and the y coordinate of the center of mass is mx over m. Mx, from what we found, is 15. Total mass is 15, that is equal to 1. So the center of mass in terms of an ordered pair equal to 29 over 15, 1. Hope this video helps.